Hello, today we discuss the Cauchy Criterion. This is another technique to determine conversions. The main statement is the following. A sequence is conversion if and only if it is a Cauchy sequence. So in order to explain this theorem, first of all, we need to know what does it mean for a sequence to be a Cauchy sequence. Here is the definition. The sequence x equals to xn is a Cauchy sequence if for any epsilon greater than 0, there exists some h possibly depending on epsilon such that for all natural integers and m greater than equal to h, we have xn minus xm is smaller than epsilon. So the point here is that for any small number epsilon, we can choose a number h such that after the for any indices bigger than h, then the difference between two elements must be smaller than epsilon. That is, after index h, all elements in the sequence are pretty close to each other because the difference between these any two elements cannot be exceeding epsilon. And the advantage of this definition is that this definition here is not dependent on a predetermined value x, which would be the limit of the sequence. There's no mention of that x at all. And in order to appreciate this definition, let's recall the original definition of conversion. The limit of a sequence xn equal x if for any epsilon greater than 0, there exists some number k, probably depending on epsilon, such that for all number n bigger than k, xn minus x must be smaller than epsilon in absolute value. So in this original definition, we need to know the we need to predetermine the value of x. But for the Cauchy sequence, we don't. We only need to show that after y, all elements in the sequence are pretty close to each other. So here is an example. The sequence xn equal 1 over n. We're going to show that this is Cauchy. So how do we do it? We just need to interpret the definition of a Cauchy sequence. We pick some number epsilon bigger than 0. We need to find h depending on epsilon such that for integers n m bigger than h, xn, the difference of xn and sm must be smaller than epsilon. How? So xn minus sm that is exactly equal to 1 over n minus 1 over m. So by the triangle inequality, this absolute value is smaller than equal to 1 over n plus 1 over n. So this is the triangle inequality we discussed in the previous chapter. Then because h, n, and m bigger than h, 1 over n is smaller than equal to 1 over h. and 1 over m is smaller than equal to 1 over h. So together, they must be smaller than equal to 1 over h plus 1 over h, which is 2 over h. And we would like to choose h so that this number is smaller than epsilon. So actually, the thinking process here allows us to tell us to how to choose h. Precisely, we choose h to be equal to 3 over epsilon, for example. Then 2 over h going to be equal to 2 over 3 over epsilon, which is going to be 2/3 of epsilon, which is essentially smaller than epsilon. So the choice of h here is not unique. There you might come up with different choices of h. Some would come up with 4 over epsilon, some would come up with 5 over epsilon. That's totally fine. But in order to come up with the choice of h, we need to do some algebraic manipulation in order to see what value of h is appropriate. Now we need to rewrite this thinking process as a rigorous proof. So the stuff here, this is just the thinking process. Now we're gonna have to write it as a rigorous proof. So the proof proceeds as follows. Given epsilon greater than 0, let h as depending of epsilon here equal to 3 over epsilon. Then for mn bigger than h, we have xn minus xm in absolute value equal to 1 over n minus 1 over m in absolute value. Applying the triangle inequality, this is smaller than equal to 1 over n plus 1 over m, which is smaller than 1 over h plus 1 over h, which equals 2 over h, which is smaller than 2 over 3 divided by epsilon, and by simplification, that equals to 2/3 epsilon, which is smaller than epsilon. Then the Cauchy Criterion is validated. So you see that when you write out the rigorous proof, you don't have to explain how you come up with h over epsilon. You came up with a choice of h epsilon by your thinking process, and you show that it works, but you don't have to explain how you came up with that choice. Now we have another example. Xn equal to 1 plus minus 1 to the n. And we would like to show that this sequence is not Cauchy. So in order to show that this sequence is not Cauchy, we need to, first of all, determine the negation of the definition of the Cauchy sequence. And the negation is as follows. There exists some number epsilon greater than 0 such that for every h there exists nm bigger than h such that the difference of Sn and Sm in absolute value is bigger than epsilon. So this is basically just logical reasoning, just the negation of the definition of a Cauchy sequence. Now we're going to show that the sequence here satisfies the negation statement above. So we choose epsilon equal 1. Then for every h, we choose n equal to 2k, which is bigger than h, and m equal to n plus 1, which is also bigger than h. Then xn equal to 1 plus minus 1 to the 2k, which is equal to 1 plus 1 equal to 2. Note that because the power here is 2k, an even number, minus 1 to the 2k is equal to 1. For Sm, the power here is n plus 1, which is equal to 2k plus 1. That's why minus 1 to 2k plus 1 equal to minus 1. So this is 1 plus minus 1, which equal to 0. Consequently, the difference Sn minus Sm is equal to 2 minus 0, which is equal to 2 in absolute value, and this is always greater than epsilon, which is chosen to be equal to 1. So we already saw examples of a sequence which is Cauchy and another example of sequence which is not Cauchy. Now, in order to prove the main statement, the main theorem, which says that a Cauchy sequence is convergent, we're gonna need the following lemmas. The first lemma is that a convergent sequence is Cauchy, and the second lemma says that a Cauchy sequence is bounded. So let me explain how this statement gonna imply the main results. So by lemma 2 here, a Cauchy sequence is bounded. That's why when you have a Cauchy sequence, then you're gonna get bounded, and applying the um, Bolzano-Weierstrass theorem in the previous section, we would be able to extract a convergence subsequent, and using this line of argument, we would be able to show that the sequence is convergent. So that's how everything fits together. Now let me explain the proof of the first lemma here. We want to show that a convergent sequence is Cauchy. So in order to do that, we need to validate the assumption of a Cauchy sequence. That is, given epsilon greater than 0, we need to find h such that certain things is true. Now, since the sequence is convergent, we know that if the limit is equal to x for some real number x. By the definition of convergence, there exists some k depending on epsilon such that for n bigger than k, Sn minus s here must be smaller than epsilon divided by half. We then choose h equal to k. Then for any indices, for any index nm bigger than h, we have the difference Sn minus Sm equal to Sn minus s plus s minus Sm. Applying the triangle inequality for this expression, it is smaller than equal to Sn minus s in absolute value plus s minus Sm in absolute value. Because h, n, and m here is bigger than h, by the definition, by the choice of h and k as described above, h difference Hn minus x and Hm minus x here is smaller than equal to epsilon divided by half. So together, it is smaller than epsilon divided by half plus epsilon divided by half, which equals epsilon. Now, this is exactly the condition of a Cauchy sequence. That's why the Cauchy definition is validated. So that's how we prove lemma 1. For the proof of lemma 2 and the general statement, you can read the textbook. Here, I would like to give an example of how how the Cauchy criterion is very important. Let X be a sequence given as follows: x1 equal 1, x2 equal 2, and xn going to be equal to 1/2 of xn minus 1 plus xn minus 2. So this is a sequence given by a recursive definition. By your previous experience, you would expect that we're going to proceed by induction and hope that this sequence is monotone. And then we can use the monotone convergence theorem to conclude that the sequence is convergent. However, by a very simple calculation, you see that x1 equal 1, x2 equal 2, x3 going to be equal to 1/2, 1 plus 2 equal 3/2, x4 going to be equal to 1/2, 3/2 plus 2 equal to 7/4. So 1 is increasing to 2, but 2 is decreased to 3/2, and 3/2 increase to 7/4. So this sequence in general is not monotone. That's why all the interesting theory about monotone sequence is not applicable in this situation. And the only way to show that the sequence is convergent is by the Cauchy definition. And we're gonna follow a very similar pattern. We prove by induction that the sequence is Cauchy. We start with the base step and then we follow up with the induction hypothesis and using the triangle inequality to go from the induction hypothesis to the +1 step. And that's how we show that the sequence is convergent.